In this video I'm going to show you how to balance chemical equations. There are 4 examples, and as we progress into this video, the examples increase in difficulty. This tutorial will also give you tips and tricks on how to balance the most challenging chemical equations. Here are the parts of a chemical equation, the reactants on the left side and the products on the right. The subscripts gives us the ratio between the elements making up a compound. In other words, it gives us the composition of a substance. In a balance equation, the coefficient is the number of molecules of a particular compound that have reacted or that have been produced, and this is the number we are going to be working with when balancing chemical equations. Before we start, we need to remember the following important points. First, the total count for each type of element must be the same on the reactant and the product side of a chemical equation. This is stipulated in the law of conservation of mass, which states that matter cannot be created nor destroyed in a chemical reaction. It can only be transformed from one form into another. Second, we can only balance the equation by adding or changing the coefficients. We cannot change the subscripts in a chemical formula because this will change the composition of a substance. We also cannot add molecules or atoms that are not in the original equation. First, we start with a simple equation, the combination reaction between hydrogen and oxygen to form water. It is helpful to make an inventory of the atoms using a table or something similar. This is especially true for those who are just learning to balance chemical equations. In this example, there are 2 hydrogen atoms and 2 oxygen atoms on the left side of the equation. And there are 2 hydrogen and 1 oxygen atom on the right. When balancing a chemical equation, start with the element or elements that are present in the least number of molecules. Here, hydrogen appears in elemental form and as part of the water molecule. Oxygen also appears in elemental form and also as part of the water molecule. Since both hydrogen and oxygen appear twice in the chemical equation, in a sense we can start with either, but since hydrogen is currently balanced, we will balance oxygen first. To balance oxygen, we can add the coefficient of 2 beside water. Remember to always multiply every subscript in a molecule with its coefficient. Hydrogen has a subscript of 2 in water, and multiplying this with its coefficient of 2, will give us 4 hydrogen atoms on the right side of the equation. On the other hand, oxygen has a subscript of 1 in water, multiplying this by 2, will give us 2 oxygen atoms. We now got 2 hydrogen atoms on the reactant side and 4 on the product side. We can balance that by multiplying the hydrogen molecule with a coefficient of 2, giving us 4 hydrogen atoms on the reactant side in a balanced equation. Although it is not necessary at this example, there is one important thing to consider when balancing chemical equations. It is good practice to reduce the coefficients in a balanced chemical equation to their lowest ratio. After a quick inspection, if you find that each and every coefficient has a common factor, it means we can divide each of these coefficients further by using the largest number possible. In our second example, we have 2 carbon, 6 hydrogen, and 2 oxygen atoms in the reactant side. And on the product side we have 1 carbon, 2 hydrogen, and 3 oxygen atoms. There are 3 oxygen atoms on the product side because carbon dioxide has 2 oxygen atoms, and water has 1 oxygen atom. Adding the 2 gives us a total of 3 oxygen atoms. You will notice that carbon and hydrogen are both present in 2 different molecules each. Carbon, in ethane and carbon dioxide, and hydrogen, in ethane and water. Meanwhile, oxygen is present in 3 different molecules, as elemental oxygen, in carbon dioxide, and in water. Besides being part of 3 different molecules, there is another reason why we have to balance oxygen last. It is because it appears by itself in elemental form. As will be our practice, any element that occurs in an uncombined state, that is in elemental form, like oxygen in this example, will be balanced last, even if it is present in a fewer number of molecules than the other elements. Since both carbon and hydrogen appear twice in the chemical equation, we can start with either of the 2. In this example, we will start with carbon by going from left to right. There are 2 carbon atoms on the left side of the equation and 1 on the right, we can therefore multiply carbon dioxide with a coefficient of 2. We now have 2 carbon atoms on both sides of the equation. It also gives us 5 oxygen atoms on the right side of the equation. We got this number by first multiplying the subscript of oxygen in carbon dioxide, which is 2, by its coefficient, to give us a count of 4 oxygen atoms. Then we multiplied the subscript of oxygen in water, which is 1, with its coefficient, to give us 1. Adding the numbers 4 and 1 gives us a total count of 5 oxygen atoms. Next we will balance hydrogen. We can do that by adding a coefficient of 3 beside water, giving us 6 hydrogen atoms on both sides of the equation, as well as 7 oxygen atoms on the right side of the equation. Just like before, we multiplied the subscript of oxygen in water with its coefficient, 3 in this case, giving us 3 oxygen atoms. Since the coefficient of carbon dioxide has remained unchanged, there will still be 4 oxygen atoms from carbon dioxide. Adding 4 and 3 gives us 7. We only have oxygen left unbalanced. Usually, it makes it a lot easier to use a fraction as a coefficient in cases where it is not possible to use an integer without having the need to change multiple other coefficients simultaneously. The trick here is to divide the number we need, in this case 7, with the subscript of that element where the coefficient is to be multiplied, which is 2, giving us 7 halves. Now we have a balanced chemical equation. We want whole number coefficients in a balanced equation. To remove a fraction, if it is a balance equation like in this case, we multiply all the coefficients with the denominator of the fraction. For partially balanced equations, we only need to multiply the coefficients of molecules with elements that are already balanced, and will be affected if a coefficient is changed from a fraction to an integer. In this example, we can remove the fraction by multiplying all the coefficients by 2, giving us a coefficient of 2 for ethane, 7 for oxygen, 4 for carbon dioxide and 6 for water. Now let's count the number of atoms for each element. On the reactant side, multiplying the subscripts of carbon and hydrogen in ethane by its coefficient of 2, gives us 4 carbon atoms and 12 hydrogen atoms. Multiplying the subscript of oxygen by its coefficient of 7 gives us 14 oxygen atoms. On the product side, multiplying the subscript of carbon in carbon dioxide by its coefficient of 4, gives us 4 carbon atoms. Multiplying the subscript of hydrogen in water by its coefficient of 6, gives us 12 hydrogen atoms. As for oxygen, multiplying its subscript in carbon dioxide by its coefficient of 4 gives us 8 oxygen atoms. Multiplying its subscript in water by its coefficient of 6 gives us 6 oxygen atoms. Adding the two numbers, gives us a total of 14. Before we start on our third example, let me discuss a very helpful tip regarding polyatomic ions. When balancing chemical equations involving polyatomic ions such as sulfate, hydroxide, phosphate, ammonium, and carbonate, it is best to treat any of these ions as one group or as one distinct unit. For more examples of polyatomic ions, refer to any general chemistry textbook. Treating a polyatomic ion as one unit makes it less complicated and easier for us. We have to keep in mind though that any polyatomic ion that we need to balance, has to appear on both sides of the equation in exactly the same state or form, like sulfate in this example. We also have to make sure that an element that is both part of a polyatomic ion as well as of other molecules, can be balanced independently of each other, or else we cannot consider the polyatomic ion as one unit and we have to balance the elements individually. Going back to our third example, on the reactant side, we have 2 hydrogen atoms from sulfuric acid and 3 from boric acid, for a total of 5 hydrogen atoms. There is also 1 sulfate ion, 1 boron, and 3 oxygen atoms. Notice that I did not include the oxygen found in sulfate in the total count for oxygen atoms. As we have discussed earlier, we will treat the sulfate ion in this example as one unit, distinct from other oxygen-containing compounds in the chemical equation. On the product side, we have 2 boron atoms, 3 sulfate ions, 2 hydrogen atoms and 1 oxygen atom. In this example, both sulfate and boron appear the least number of times in the chemical equation, twice for sulfate and twice for boron. Just like before, we will go from left to right, so we will start with sulfate. Multiplying sulfuric acid with the coefficient of 3 will give us 3 sulfate ions on both sides of the equation. It will also give us 9 hydrogen atoms on the reactant side, 6 coming from sulfuric acid, and 3 from boric acid, for a total of 9. Next, we will balance boron by multiplying boric acid by 2, giving us 2 boron atoms on each side, and 6 oxygen and 12 hydrogen on the reactant side, 6 hydrogen atoms coming from sulfuric acid and 6 from boric acid for a total of 12. We are now left with only hydrogen and oxygen to balance. We can balance both by multiplying water with a coefficient of 6, giving us 12 hydrogen and 6 oxygen atoms on both sides of the equation. We now have a balanced chemical equation. For difficult to balance equations like the one above, a knowledge of algebra, specifically the manipulation of simple linear equations, will be of great help. By following a few simple steps, we can balance most if not all of the chemical equations, including the extremely difficult ones. Initially, the whole process can be daunting, but the more you practice, the easier it gets and the faster you get at doing it. This approach works well when dealing with difficult to balance chemical equations, and is actually faster than the traditional approach of trial and error when dealing with these kinds of chemical equations. Going back to our example, notice that even though the nitrate ion is present on both the reactant and the product side of the equation, we cannot balance it as one unit. We have to balance the nitrogen and oxygen in nitrate separately. The reason for this, as we have discussed earlier, is that nitric oxide also contains nitrogen and oxygen, and there is no other nitrogen or oxygen containing compound on the reactant side that we can use to balance the nitrogen and oxygen in nitric oxide other than nitric acid. The first thing we need to do here is to represent each coefficient with a variable. In this example we are going from left to right using the letters A, B, C, and so on. Next we are going to write a linear equation representing each and every element present in the chemical equation. For copper, our equation will be A equals C. Looking at copper in the chemical equation, you will notice that elemental copper has a subscript of 1, multiplying it by A, its coefficient, gives us A. On the right-hand side of the equation, copper also has a subscript of 1 in cupric nitrate, multiplying it with its coefficient C, gives us C. Because it is an algebraic equation we need to replace the arrow with the equal sign. For hydrogen, the equation is B equals 2E. Since it is very similar to the previous equation, I would not be explaining it further. For nitrogen, the equation is B equals 2C plus D. Looking at nitric acid, nitrogen has a subscript of 1, multiplying it with its coefficient of B, gives us B. On the product side, nitrogen has a subscript of 1 in cupric nitrate, multiplying it by 2, the subscript outside the bracket, gives us 2. Multiplying it further by the coefficient C, gives us 2C. Always remember, that subscripts within a bracket has to be multiplied with the subscript outside of it. In nitric oxide, nitrogen has a subscript of 1, multiplying it with the coefficient D gives us D. Lastly, for oxygen, the equation is 3B equals 6C plus D plus E. In nitric acid, oxygen has a subscript of 3, multiplying it with the coefficient B gives us 3B. On the product side, oxygen has a subscript of 3 in cupric nitrate, multiplying it with the number outside the bracket, which is 2, gives us 6, multiplying 6 by its coefficient gives us 6C. In nitric oxide, oxygen has a subscript of 1, multiplied by its coefficient of D, gives us D. In water, oxygen has a subscript of 1, multiplied by E, gives us E. For easy reference, we are going to label these equations as 1, 2, 3, and 4. Before we start the elimination process, it is very helpful if we first count the number of linear equations a particular variable is in. For a, it is only in one linear equation. Equation 1. For variable b, it can be found in equation 2, 3, and 4, for a count of 3. For variable c, it can be found in equation 1, 3, and 4, also for a count of 3. For variable d, it can be found in equation 3 and 4, for a count of 2. And lastly, for variable e, it can be found in equation 2 and 4 for a count of 2. By keeping track of the number of linear equations a particular variable is in, it makes the elimination process easier to follow. This is especially helpful when we have to deal with many linear equations and variables. Now we are ready to eliminate one variable at a time until we are left with only one or two variables. We will start by eliminating variables that are found in only two linear equations. Based on this, we can see that there are two variables, d and e, that we can eliminate at this time. We will eliminate e first by subtracting equation 2 from equation 4. To eliminate e we need to multiply equation 4 with the number 2, giving us 6b equals 12c plus 2d plus 2e. Subtracting the two equations, we get equation 5. Always remember, we can only use a linear equation once in an algebraic operation. We can therefore cross out equation 2 and 4 from the list. After each elimination process, also remember to update the counts for the variables. The new count for b is 2. It is present in equation 3 and 5. Since we have already eliminated the variable e, we can cross it out from the list. The count for the rest of the variables remain the same. We currently have two variables that we can eliminate next. B and D. We will be picking D in this example. To eliminate D we will subtract equation 3 from 5, but first we have to multiply equation 3 by the number 5, giving us minus 5b equals minus 10c minus 5d. Cancelling 5b out, and subtracting the rest, we get equation 6. We can now cross out equation 3 from the list. We also need to update the counts for the variables. The new count for c is 2. It is present in equation 1 and 6. For variable d, the new count is 1, and is only present in equation 6. Since we have already eliminated variable b, we can cross it out from the list. We are now left with just one variable that we can eliminate. Variable c. We can do that by subtracting equation 1 from equation 6. First we have to multiply equation 1 by 2, giving us minus 2a equals minus 2c. We can then cancel 2c out and subtract the rest of the variables, giving us equation 7. By multiplying equation 7 by minus 1, we get 2a equals 3d. We can just as well write equation 7 as 3d equals 2a by rearranging the equation, and it won't make a difference. By crossing out equation 1, we are left with only one linear equation. Equation 7. And with variable c eliminated, we don't have any more variables that we can eliminate, as both variables a and d only have a count of 1. We are now ready for the next step. Once we arrived at the final equation, which is equation 7 in this case, we will assign an arbitrary number to one of the variables. We can start with any variable, the order will not make a difference. In this example, we will assign a value of 1 to variable a. 1 is a convenient choice, being the lowest positive number. Substituting a with 1 in equation 7 gives us 3d equals 2. Dividing the equation with 3, gives us d equals 2/3. We now have known values for variables a and d. We can now substitute the values of variables a and d in one of the linear equations on the left. Choose a linear equation where we can substitute each and every variable in the equation with a known value and left with only one unknown variable. Of the four linear equations, only equation 1 meets this criteria. Although we can substitute variable d in equations 3 and 4 with a value of 2/3, we will still be left with two or more unknowns to solve. Since c is equal to a in equation 1, substituting a with the value of 1 gives us c equals 1. We now have known values for variables a, c, and d. We can substitute variables c and d in equation 3 with 1 and 2/3 respectively to solve for b, giving us 8/3. Lastly, we are going to solve for variable e by substituting the variables b, c, and d in equation 4, with 8/3, 1, and 2/3 respectively, giving us 4/3. We now have solved the values for all the variables. Next, we are going to substitute the values of the coefficients with the values of their corresponding variables. A with the value of 1. B, with the value of 8/3. C, with 1. D, with 2/3. And E, with the value of 4/3. To have whole number coefficients, we have to multiply all the coefficients with the number 3, giving us the final coefficients of 3, 8, 3, 2, and 4 respectively. Notice that the coefficients do not have a common factor that we can divide them further. So this will be our final balanced chemical equation. I hope that you learn a lot from this tutorial, and if you have any suggestions to make this tutorial better, please don't hesitate to write in the comments section. Good luck!